Chapter 5, Series Circuits. So today we're talking about a series circuit. A series circuit is described as a circuit where there's only one path for current to flow. Current leaving the positive terminal of the source, flowing through all the conductors and the loads in the loop, and returning to the negative terminal of the source. That's defining a series circuit. A series circuit representation is the most common representation for all circuits. That is to say that we can take the most complex circuit that we can think of and represent it as one load in series with a source as a simplified circuit. So the most simplified circuit is a circuit that's represented as a series circuit. And as we go forward and we study different circuit connections like parallel and combination circuits that combine both series and parallel components, we'll see how it can all be simplified to a simple series circuit with a load connected in series with a source. So that's what we're looking at today. Two elements are said to be in series when they are connected at a single point and there are no other current carrying connections at this point. So when we're talking about a connected at a single point, a point in a circuit means there's no current division. A node means there's current division. So we would find nodes in a parallel circuit where we have current division, where the current splits between two directions. In a series circuit, we have loads connected at a single point where there's no current division because there's only one path for current to flow. And notice how here it says no other current carrying connections at this point. A series circuit is constructed by connecting various elements in series. Current will leave the positive terminal of the voltage source. So it'll leave the positive terminal of the voltage source, move through the resistors, and return to the negative terminal of the source. So we know that that is our conventional current. Current flowing through a circuit is similar to water flowing through a pipe. We use that water analogy in our last couple of presentations, and we must have the same flow throughout the whole circuit. So it doesn't matter where you were to check the flow in that water circuit that we used in the last presentation, the flow would be the same. So this is an element of or a property of series circuits that's used all the time. For the series connection, we have identical current everywhere in the circuit. And this is very important because it doesn't matter whether we're talking about circuit design, circuit troubleshooting, circuit analysis, problem solving. When we're looking at a series circuit, you can be pretty much guaranteed that part of the solution, part of the determining the missing value or the missing part of a design is going to be centered around the fact that for a series circuit, the current is identical everywhere. And if you can remember this, when you work on ELAB number 4, that I give you as an assignment for designing a circuit based on certain requirements, you will find that because it's a series arrangement, you want to key in on the fact that you have identical current everywhere in a series circuit for your design. That's going to really unlock the process of designing it properly. So if you can remember that, that's for ELAB number 4. So the laws, theorems, and rules that apply in DC circuits also apply in AC circuits. So what it means is any of these laws of Ohm's law, Kirchhoff's law we're going to look at today, Watts's law, all these laws and relationships we've covered, it should be stated that it doesn't, these laws don't change when you involve an AC circuit. So here we see an example of a 3 resistors connected in series to a source. Notice how the direction of current is what develops a voltage drop. And it's that voltage drop that has a polarity based on the direction of current. So we have current entering the positive terminal and exiting the negative. Okay, this is the current direction through R2, entering the positive terminal, exiting the negative. This is the direction of current through R3, entering the positive and exiting the negative. We can confidently say that will be the voltage drop polarities for each one of those resistors. Of course, we can't calculate the magnitude yet because we don't have a value of resistance and we don't have a value of current. We can't calculate the IR drop yet, but we can say that this can be labeled VR1, VR2, and VR3. So when it comes to these loads connected in series, and we'll use the example consistently of 3 loads, it says the summation of voltage rises, which are source voltage, and voltage drops, which is load voltage and source voltage, around a loop is equal to 0. Now, what that really means is there's a couple of different ways that can be expressed. We could move all of the voltage drops on the other side of the equal sign, and we could say that E total equals V1 plus V2 plus V3. This is really saying the same thing. It's just saying that a voltage drop has a polarity opposing the source. So if we were to go back here, look at these voltage drop polarities. This is a minus plus. If this was a series aiding connection, that is bringing the voltage up, it would be a plus to minus connection like we do when we connect batteries in series to increase their voltage. This is not a plus to minus connection. This is a plus to plus connection, which is called an opposing connection. So that means this voltage opposes the source. This voltage opposes the source, and so does this one. So when they're added to the source in series, they have to be added as a negative value. So that's why you see what you see in this first equation. You could think of it this way. E total plus minus V1 plus minus V2 plus minus V3 equals 0. The voltages in the loop are balanced to give you 0. All we did here was move all the drop voltages on one side of the equal sign and keep the source voltage or the voltage rise on the other side of the equal sign. Another way of stating this equation is, or expressing this equation, is called Kirchhoff's voltage law. Okay, so and we often just call it KVL. It really says the summation of all voltage rises is equal to the summation of all voltage drops around a closed loop. So if we had multiple sources like E1, E2 plus E3, that would apply. All of our voltage rises on one side, all of our voltage drops on the other side. Kirchhoff's voltage law says for a purely series circuit, those two quantities have to be equal. And we can use that to prove an unknown value, consistently. So let's say we had something like 12 volts for V1. V2 is 4 volts. V3 is 6 volts. Well, then together we would have a total of 22 volts. We know that each side of the equal sign has to be balanced. So if we were to say that E1 was 10 volts, E2 was 6 volts, we would be able to conclude that the missing value of E3 would have to be 22 volts minus 16 volts to give us 6 volts. So this is an example of where Kirchhoff's voltage law could have been used in that example to determine an unknown value of source voltage, knowing that it would be 6 volts. So, like it says, almost all complicated circuits can be simplified. And so when it comes to a series circuit, we said the series circuit was the most simplified example of any circuit. And we'll do that in circuits going forward. We'll simplify a circuit right down to an E total value, indicating the total motivating force, or the total applied voltage, and in series with the total amount of opposition, where we'll call that R total. So in a simplified circuit, you have your total amount of motivating force as E total, your total amount of opposition as R total, and then you could conclude or calculate a total value of current for a circuit that is a simplified. So this could be a simplified example of a complex circuit, simplified circuit. Okay? So for a series circuit, we've already determined that the sum of the voltage drops will equal the voltage rise, or the sum of the voltage rises. So V1 plus V2 plus V3 equals E. So we proved that. Then what we are doing is saying each one of those voltages can be expressed as an IR value. So it means that our current, which is all the same, because we know that I total equals I1 equals I2 equals I3. We know that for 3 resistors in series, the current of each one is going to be all the same, and it's also going to be equal to the total current. So if that's the case, then we can say that the same value of current I is being multiplied by R1 to give us V1. The same value of I is being multiplied by R2 to give us V2, V3, and so on. And then further, we know that our E total value is an IR value that can be represented as I total times R total. That's our IR value representing our total applied voltage. So it means that we can actually remove the I value as a common factor from each one of these terms, right? So that's what we did here. We removed the I from each one of those terms to give us this. And then likewise, you could remove the I from this term and give you R total. So notice how we can say that gone, gone, and that leaves us with an equation for total resistance in series. So for total resistance in series, then, we could conclude from what we've derived here that R total equals R1 plus R2 plus R3. You simply just add the opposition together in series to give you total opposition. When it comes to power in a series circuit, all of the power equations that we've learned about still apply. So when it comes to power using voltage and current, we have V times I. Voltage and resistance, V squared over R. When it comes to current and resistance, I squared R. So if we're talking about PR1 then, what would that mean? VR1 multiplied by IR1 would give you power. VR1 squared over R1 is going to give you power as well. You get the idea. Let's do one more. What about P total? P total would be E total times I total. Okay, likewise E total squared divided by R total. Using total values, they are going to give you a total power. All right, here's something else. Now this equation is actually not just applicable to series. This is for all circuits. But it certainly applies to series. And if you have individual powers dissipated, you can simply add them all up to give you total power. So if you have PR1, PR2, PR3, add them all together, what's that going to give you? Total power. How could it be confirmed? Is by using one of these equations. So power is the same, or calculated the same in a series circuit. So voltage sources in series, a lot of this stuff is stuff that we've looked at previously. When you're connecting voltage sources in series, make sure you take the polarities into account, because we could either have a series aiding connection, which is what? Plus 2 minus, plus 2 minus for a series aiding connection, or you could have a series opposing. And if you were to have a series opposing, you would have plus 2 plus. And that would result in a potential that is working against the overall potential. So we've mentioned that and talked about that and had that discussion already, but we can review it, and we will be reviewing it when we do problems in this chapter, because we will see voltage rises connected in series in a loop, and we have to add them together to give us our total motivating force, or our total E total value. So changing the order of components within a series circuit, is that going to change the operation? The answer is no. It doesn't matter what order the components are in the loop. It'll operate the same, it'll dissipate the same amount of power, it'll do the same amount of work, it'll draw the same current, everything will be the same. So based on the fact that we can change the order of series components for analysis and troubleshooting and for determining unknown values, we will often redraw a circuit to make it easier to interpret or understand. And this is something we do in circuits all the time. And as they get more complex, redrawing a circuit is going to be a more and more valuable tool. So right from the beginning, even for the most simple circuits, we want you to get into the practice of redrawing the circuit. A standard for redrawing the circuit is to put all voltage rises to the left and all loads to the right. So let's say in this case we had 3 loads and 2 sources, E1, E2, R1, R2, and R3. That could be an example of a circuit of where we redrew it to put all motivating force to the left, all voltage drops to the right, and represent the circuit as a simple series circuit. Now, of course, you just come up with an E total value that is equal to, as you know, E total here would equal E1 plus E2. Notice how I said plus E2, because it's a series aiding connection. We know that when it comes to the resistance of that series connection, R total would be R1 plus R2 plus R3. We add resistance together to give us our total. We can say we have E total as calculated in series with R total. So in series with R total then becomes our simple series circuit arrangement. So now we come to something called the voltage divider rule. Now I'm just going to add the equal sign that is missing in these presentations sometimes for some reason. So Vx equals Rx over R total times E. Now here's where I want to talk about resistance, right? So I'm going to use a pie chart to represent the total resistance in the series circuit. Now let's say we have a resistance such as this, where this whole pie is making up a value of R total. And we have R1 and R2 and R3 as part of that total resistance. We know the total resistance is determined by R1 plus R2 plus R3. In this case, we can see that R1 is equal to the value of R2, and R1 added to R2 will equal R3. If we were to add R1 to R2 to R3, we would equal R total. This is the distribution of opposition in that series arrangement in this example. But remember, we have a common quantity in this series circuit as well, and that is that I total equals IR1 equals IR2 and equals IR3. Based on the fact that current is all the same and that the voltage drops that give you a V total value or an E total value, E total equals IR1 plus IR2 plus IR3 as the voltage drops. This is Kirchhoff's voltage law. Because we have the same value of current, we can take it out of each one of these factors to tell us that with that being the case, each one of the voltage drops has to be directly proportional to the value of resistance. So what does that mean? We can say that because each one of these is being multiplied by the same value of current, IR1 has to equal IR2. It's proportional to the resistance. IR1, which is the voltage of R1, added on to IR2, which is the voltage of R2, has to equal R3. So therefore, what it means is if we make a fraction of resistance 1 with respect to R total, that'll be the same fraction that makes up our voltages when it comes to E total. VR1, VR2, and VR3 are going to have the same proportions. So it means we can make a voltage divider rule that says VR1 equals R1 over R total as a fraction multiplied by E total. And that's what we see here. So, yeah, this voltage divider rule application means we actually don't need to have a value of current in order to predict what voltage drops will be. So if let me just give you an example. Without calculating current, if I said this was 120 volts and there was two resistors connected to 120 volts, R1 and R2, and I told you R1 was equal to R2, you could tell me that VR1 would be equal to 60 volts and VR2 would equal 60 volts. Based on just the quantities of resistance connected in series and without even knowing the current. If the resistors were equal, they would have equal voltage drops based on the voltage divider rule. Okay, so let's just take a look at this slide. If a single resistor is very large compared to the other resistors, then the voltage across that resistor will essentially be the source voltage. So this really is going back to our open circuit voltage as well. So let's say we had a circuit with an open circuit in it like we investigated in our E-Lab. If this is infinite resistance, and this is even 100 k ohms, infinite resistance is more than 100 times any value. And so as a result, we would say that the source voltage would be present across that infinite resistance, and certainly that's what we found is when we investigated E-Lab 1, is that when we had an open switch, we found the source voltage across it, and there was 0 volts across the load. Okay, so 100 kiloohms is very small compared to infinite ohms. So as a result, the voltage is 0. Now, Here's one statement that we'll use a lot, and it's really applicable when we look at the lab and practical circuits, and when we look at the E-lab and do virtual measurements. If a resistor is more than 100 times larger than another resistor, then the smaller resistor can be ignored or neglected. So it's the same idea in measuring voltages. If you were to measure the voltage around a loop and you found that a voltage measured in series was less than 1/100th of the source voltage, you could ignore it, because the source voltage is the largest voltage in the circuit. Any values that are less than 1/100th or less than 1% of that total source voltage can be ignored, can be recorded as zero, right? So those voltages that are less than 1/100, it's called the 100 times rule. Any values less than 1% of the maximum values can be ignored and recorded as a zero value. All right, here's where we're going to talk about circuit ground. This often becomes a little bit of something that's difficult to relate to or understand. And the funny thing about it is, it seems like the more experience you have with electricity, the harder it is to understand this. If you come in here completely as a beginner, you'll listen to what I have to say, and you won't be confused if you just listen to what I have to say. When it becomes confusing is for people such as electricians and people who have had previous experience with electricity. They have a real misunderstanding of what the true definition or meaning of ground is. So if we can just start with that statement and realize we're going to back up and say, what is circuit ground? Circuit ground is simply an assigned point of reference. Okay, I'm going to say that again. Circuit ground is simply an assigned point of reference. So let's say we go back to E-lab number 1 where we had several points, A, B, C, D, and I just said, I'm going to assign point C as reference. You will use that as reference for all voltage measurements. Your black lead will always be on point C. I'm going to make that the point of reference for every voltage that you read in this circuit. That could be also called ground if I chose to call it ground. It was called point C in my example, but making it a common point of reference, it could have been referred to or called ground, and I could have assigned it as something called ground as a common point of reference in a circuit. Now, when it comes to practical circuits now, we can take that further. Sometimes your common point of reference in a circuit is something called chassis ground. An example of chassis grounds are things like your audio amplifier or a power supply in a computer, or the frame of your vehicle, your car or your truck. The chassis itself can be used to conduct electricity back to the source. So we could have something like this. A source connected to a load, R total, with, and I'm sorry, I should do a better job of my diagramming. I should have shown this ground like that, sorry. Okay, so you could have and even better, because I'm referring to chassis ground, I should have showed it like this. Okay, so let's just, and I don't have my eraser up and I'm not going to do that, so let me start this one more time. Sorry about this. So chassis ground, R total, and E total. How does the return path or the closed loop occur here for this to be a closed loop for current to flow? Well, what it means is there's a actual connection made by the conductive chassis that allows this loop to be closed. So what do we have? We actually have a connection made by the conductive chassis that becomes a common point of reference. Common point. It's chassis ground. And it's also the conductive return for current to end up back at the voltage source. This is called chassis ground. It becomes both a common point of reference for all voltage. It becomes a common point of connection for loads that are in a system that has chassis ground. In a system that has chassis ground, sometimes it can look like a load has only one wire connected to it. It has a positive lead connected to it, but then it's actually mounted to the chassis, and so you don't see evidence of a second wire to return the current to the source. That's because the current is being returned through the conductive chassis. Okay, so hopefully that makes sense as far as circuit ground and chassis ground. It's because of this slide right here that a lot of people with previous experience in electricity are confused by the true meaning of ground. Now, in this example, we are talking about safety ground. And safety ground is part of our power system, part of our electrical grid, and it's there to prevent people from getting shocked and losing their lives. And the protective ground or safety ground is there on every receptacle or every appliance, and it's used whenever you're working with an appliance or a tool or an electric device that has a metal chassis or a metal body or a metal handle, or there's a risk of shock. And remember in the lab, day one, when we took the center conductor or the center prong of a plug on your power supply and used our ohm meter to measure the resistance between it and its chassis, its cover, the screw on that cover. We found 0 ohms of resistance, a short circuit to that cover. And why is that? Well, it's such that if we were to get a AC line voltage and it would end up touching that chassis, we would immediately short the AC line to this protective ground, which finds its way back to the power system's source and shunts all the current away from you and being able to shock you with that voltage, and it should immediately trip the breaker or the overload protection. So the whole idea of the safety ground in this system is what protects you from getting shocked, because it shunts any of that dangerous current to what's called safety ground, which has its way back to the power system ground connection that's common for all of the grid, and overload protection trips, and you're safe from any issues. So earth ground is physically connected to the earth by a metal pipe or rod. If you were to look at the bare wire in your electrical panel at your home and follow it and trace it, you'd find it going outside and it'd be driven into the ground. It's called a ground rod, and every power system is grounded to the earth in some way or another in order to have that safety ground. If a fault occurs within the circuit is redirected to earth. The current is redirected to earth. And when redirected, it's a high current, and that's where the overload protection comes in and trips the breaker. And voltages are often measured with respect to ground. So we can use this ground as a reference, absolutely. A lot of times in AC, voltages are just referenced from line to line. So we would have 120 volts here. across these two conductors. But there's no doubt with ground in the circuit, you can assign any reference and you could measure each one of these voltages with respect to ground. So hopefully that helps. That's safety ground. But other than that, don't be confused by anything when it comes to ground in any of the examples that we look at in this course. Understand ground as simply a point of reference, an assigned point of reference. And if you remember that, you won't make any errors. So let's take a look here. We have ground as a single point of reference in circuit A. And it should be understood that because that's the same point, so if I was to just arbitrarily give that a point called A, I would have to give this a name A as well. It's the same point. Ground is the same point. And if it's the same point, you could connect it with a line. And that means if you wanted to show the circuit here as a closed loop circuit, you can freely decide to connect ground symbols together to give you a closed loop. But what you do need to understand is when making voltage measurements, if you're referencing ground, and I'm just going to put a B here and a C here, if you're referencing ground such as a single subscript voltage like VC or VB, you need to understand that the other point of measurement that's left out of this measurement is ground. And so if we called it A here, it'd be equivalent to VCA and VBA because we called ground A. Okay, that's the same circuit that we have here. There's absolutely no difference in power dissipation in anything about these two circuits. This is the same circuit. This is the same circuit. It has the same power dissipation, the same direction of current, the same current flow. The only thing that's changed is here, the point of reference is a different point of reference than here. Right? Notice how here the positive terminal of the source is grounded. You can see the positive terminal of the source is grounded. Over here, the negative terminal of the source is grounded. And the only thing that would be different from the first one to the last one is the point of reference. Otherwise, everything else about that circuit is the same. Same direction of current, same powers dissipated, same voltage drops, same R total value. Okay? So that is ground. So double subscripts then, when we're talking about double subscripts, we talked about this in ELAB. The voltage VAB is saying what is the voltage at point A with respect to B. B is the second letter, becomes the reference. If A is at a higher potential than B, then the voltage is positive. If B is at a higher B is at a higher potential, the voltage is negative. So notice how here it says if A is higher than B, it's positive. If B is higher than A, it's negative. Okay? So in this case, we could determine all values of double subscript. And let's just take this CD one. Obviously, if we said VCD, we would start at D because that's our reference. We would move our way to point C and see that our magnitude is 25 volts. So we'd put in 25 volts. And we can see that point C is more positive than point D, so we'd label this plus 25. VDC would be the opposite, wouldn't it? We would start at point C, we would work our way to point D, we would see that we have 25 volts of magnitude, but that point D was negative of point C, and that would have to make this minus. So to determine the correct polarity, first calculate all the voltage drops across the components. So calculate all your voltage drops, all your magnitudes. Then assign your polarities. And how do you assign your polarities? Based on the direction of current. If I have a voltage drop and I tell you current is in this direction, you know the voltage drop polarity enters, or current enters the most positive polarity of the voltage and exits the negative. So that makes this the polarity for V. As you go around a circuit, add the gains and subtract the drops. Pretty straightforward. Single subscripts. Single subscripts are always with respect to ground. So if you don't see this symbol in a circuit, single subscript has no meaning. Without seeing that symbol, single subscript has no meaning. It's always with respect to ground. So when it comes to single subscripts, we can use those to determine a VAB value. Okay? When it comes to single subscripts, we can use those to determine a VAB or double subscript value. It turns out that if you want to determine what a value of VAB is as a double subscript, and you have single subscript values, you can determine that by subtracting the two. But it's important you subtract them in the right order. VAB would be VA minus VB. VBA would be VB minus VA. There's a difference. Okay? So if we look here, we can assign these points on this diagram. Plus 5 volts. Whoops. Plus 5 volts. B is plus 3 volts. And C is minus 8 volts. Those are single subscript values. So there is somewhere a reference to ground for this example. And so we have point values here, what are called point values or single subscript values for voltage. Now we can determine any of the voltage drops for these resistors based on this. So if we wanted to determine what VAB was here, what would that be? VA is plus 5 volts minus plus 3 volts to give you a total of plus 2 volts. So that means we have 2 volts here, and that our VA value is 2 volts more positive than our VB value, and we've got our VAB of plus 2 volts. You could do the same thing with VBC. So let's figure out VBC. VBC, that would be the voltage of R2, is equal to VB minus VC. VB is plus 3 volts. Now we're going to minus 8 volts. Minus and a minus equals a plus. So that's going to be equal to plus 3 plus 8 equaling plus 11 volts. VBC is plus 11 volts.